Okay, so now we have established that the sign of the Joule-Thomson coefficient, which remember it was the volume divided by the heat capacity at constant pressure, and here is T alpha minus 1. Well, the sign of this thing is determined only by what we have in the parentheses, right? So imagine that you want to use this effect to cool down a gas, okay? So what can you do then? To get an idea, let's just try to represent states of the gas in, like as usual, in a suitable representation. In this case, the PV representation is not the most suitable one. It's actually PT. Why? Because the two relevant variables in this case are P and T. Yes, sir. P and T, because this is the partial derivative of T with respect to P at constant H. Okay. So, okay, let's plot the equilibrium states of our gas that we want to cool down in this representation. And what we want to do, we want to know, is where does the coefficient vanish? Okay, so the coefficient vanishes whenever T times, and here is the coefficient of thermal expansion, which you can write, if you want, as a function of P and T. If this thing is equals to 1, then the Joule-Thomson coefficient goes to 0. So where does this happen for a real gas? Well, if you plot the curve, it looks a bit like this. Okay, I have plotted for you in the lecture notes for the specific case of a van der Waals gas. Okay, so in general, real gases also look the same, something like that. And the situation you have in practice, let's say, is that at room temperature, your gas that you want to cool down, say at room temperature, so it's sitting here, let's call this T1, and what you want to do is to reduce the temperature, okay? You know also that the atmospheric pressure has a pressure somewhere here, right? So that's the atmosphere, let's call it P2, you will see why in a moment. And that's the reference pressure, that's the lowest pressure you have around, okay? And what you can do with your gas is you can put it in a pipe and you can increase its pressure with a pump. Okay, so you can pump it up and you can increase the temperature of the gas but anywhere you like, right? Anywhere you can. But the thing is, you know that, well, I didn't tell you this, but this line here is the line where alpha jt equals 0. Under the line, okay, alpha jt is larger than 0, which is what you want. And above the line, alpha jt is smaller than 0. Okay, so you know that you can take your gas, put it in the pipe, and you can increase the pressure to any level. Let's call it P1, and then you can let go. Okay, and you can let it expand, and you can let it have a final pressure P2, which is the lowest pressure you have because it's the reference value, it's your atmospheric pressure. And you know that as a result of this, the gas will reach a temperature T2, which is lower than the initial room temperature T1. Okay, the key question here is how much lower is this new temperature? Okay, because you see, you cannot do much about the atmospheric pressure or the initial temperature you have. What you can is play around with the pressure that you put your gas to, the high pressure level, so that then when it expands, it cools down as much as possible. Okay, what would happen, for instance, if you were to compress too much and you would go above this inversion curve? Well, what happens is that instead of cooling down, your gas will heat up because the Joule-Thomson coefficient is negative above the curve. Okay, and that's not what you want. So you are restricted to play with pressure in this specific range. So this is why this curve is useful, because it tells you what is the pressure range that you can play around with to cool down the gas with Joule-Thomson process. And this curve is called the inversion curve, just because the Joule-Thomson coefficient flips sign. If you are underneath, it's positive, and if you are above, it's negative. Okay, so this is the inversion curve. And the question we have now is how to choose the pressure so that the final temperature is as low as possible. Okay, so if you remember again what the coefficient is, if you are in this kind of isenthalpic process, what happens is that dt, right, equals alpha jt dp. Why? Because alpha is the partial derivative of t with respect to p. So it's this ratio of dt by dp. And I can write it like this if I want for an isenthalpic process. And then I can integrate the two sides. Okay, so here I integrate from t1 to t2, and here I integrate from p1 to p2, right? And what this gives me is t2 minus t1 equals, well, the integral that I have written there, right? So I want to minimize this thing here. I can write t2 equals t1 plus the integral from p1 to p2, and here is alpha jt differential of p. Okay, and if you realize the only parameter that I'm playing with is this pressure. Okay, I can make it larger or smaller, but I'm playing around with it. So what I want, if I want to minimize something, as you know, okay, so what I want to take the thing I want to minimize, and I want to impose the extremum condition, okay, with respect to the parameter that I can optimize over, which is this high pressure level P1, okay, and I say this is equal to 0. But what is this derivative? Well, T1 does not depend on P1, it's a constant, so that has 0 derivative. And I have to find the derivative of this integral, okay, with respect to P1. And P1 here is a limit of integration. So remember, when you have an integral and you take the derivative with respect to the limit of the integral, then you have to use the Leibniz formula, or I'm not sure how you call it, but it's called the Leibniz formula, or the rule for taking derivatives under the integral sign, or something like that. You have the general expression in the lecture notes. It's very easy. The thing is that this derivative, it gives you this thing inside the integral does not depend on the value p1, it just depends on p, but not on p1. The upper limit of the integral does not depend on p1 either. It's only this lower limit of the integral that does depend. So the result of this derivative is minus the integrand replaced at p1, well, also t1, which is fixed, right? So this is the initial temperature, T1. And here I have to put the derivative of the lower limit of integration, P1, with respect to P1, which is 1. Okay, that's what I'm left with. So it's this minus alpha jp. And as I say, I want to impose the extremum condition. Okay, so I want to know for which values does this thing have an extremum. Okay. So what I'm saying is that alpha jt evaluated at p1, t1, has to be equal to 0 if I want to make sure that t2 is as low as it can possibly be. Okay, because that is where t2 has an extremum with respect to p1. So what I'm saying is that the actual value of the pressure that I want for my system to cool it down as much as possible is exactly lying on the curve, because that's exactly when the coefficient itself is equal to 0. Okay, that's what I'm saying. The coefficient at that specific unknown pressure has to be equal to 0. So this is the significance of the inversion curve. It tells you what is the pressure that you have to pump your gas to cool it down as much as possible. Okay, and let me just make this remark that I write about in the lecture notes, which is not all gases will be like this, right? So for instance, like I said before, hydrogen. So hydrogen at room temperature is sitting there, okay? So it's way to the right of this inversion curve. So there's really no pressure that I can pump my hydrogen up to so that it will cool down when it expands. It will always heat up, okay? So what I have to do with the hydrogen is to cool it down first so that it falls underneath the inversion curve, and I have to cool it with some other technique. I cannot use Joule-Thomson cooling, but once I have heat this this area, then I can do Joule-Thomson cooling, and then I can cool the hydrogen even further. And this is what is done actually to liquefy hydrogen, which is possible, but it is complicated. Okay, fine. So to conclude, I will just make very minor remarks about how you calculate internal energy and entropy for any real gas. We are going to do exercises about this in the synchronous session anyway, so that would be the last short video of this lecture.